Hello, Calculus 2. Area in polar coordinates. You hope there's a lot of good problems to work on. I like this one. This is kind of interesting. Between the loops. So, depends on how the question is worded exactly, so I didn't really word this one yet. But this is a nice limison that has an inner loop. And so when I'm asking for the area between the loops, I think that's obvious, but let's clarify that. So let's see, if this is a limison, you know what I want to do? I want to find the tangents at the pole. I want to sketch a graph, and my calculator would help me. But I want to set this equal to 0. I want to find the tangents at the pole. So I set this equal to 0. That was a technique we learned. I'm going to move this 8 sine theta over. I'm going to divide by 8, so sine theta is a half. And I know what that is. That's pi over 6, 5 pi over 6. Right? That's a 30-degree angle, and it's positive. Yeah. So apparently, this is this limison. It probably hits here at 4. It comes in here, and it, oops, well, just to be a little more accurate, that tangent is a 30-degree angle there. So it comes in here like this. It must do its inner loop. It comes back out like this, and it goes down probably to about 8 down here. Is that right? Or maybe even 12 down here. Huh? Doesn't really matter too much. So that's a picture of this limison with an inner loop. And we found one of the tangents at the pole, and here's the other tangent at the pole. And there's a lot of good questions. You know, let's just say, if the question was find the area of the inner loop, that's a good question, then you could try to integrate. I mean, this one equation is this whole shape. And if you just want the area of the inner loop, then you would maybe integrate from pi over 6 to 5 pi over 6. That's when it kind of goes into the inner loop. You know, if I was plotting points, when theta is 0, I guess I'm here. From 0 to pi over 6, it plots these points, and it comes into the pole at pi over 6. These are called the tangents at the pole. And then from pi over 6 to pi over 2, it's plotting these points, and pi over 2 to 5 pi over 6, it's plotting these points, and then it's coming out of the pole. It's coming out of the inner loop. And then from 5 pi over 6 all the way around to pi over 6, it would plot the rest of this limison. So I'm just speculating on some concepts. I'm sorry, I'll get focused here in a second, but I'm saying if you just wanted the area of the inner loop, that would be an integral set up from pi over 6 to 5 pi over 6. But we wanted the area between the loops, so that's not this. Between the loops, I think, again, students always ask me to clarify that. I think it's kind of obvious, but I guess there's an outer loop, and then there's this thing I'm calling the inner loop. So between the loops would be this area. And it would exclude the inner loop. So it's between the loops, and we want to exclude the inner loop. So then you might think, okay, I'll set up an integral. Excuse me. I really need this now. I'll set up an integral. You know, when you integrate, you do a half out front in polar coordinates. You square the function you're integrating. And there it is. I mean, so that's not difficult. What's difficult is usually these bounds. It takes a little thought in figuring out here. So what did we just decide? If I do from pi over 6 to 5 pi over 6, I'm doing the inner loop. I don't want the inner loop, so maybe I'll just go from 5 pi over 6 all the way around. Now you got to be careful. If you do go from 5 pi over 6 all the way around, you can't name him pi over 6. You're increasing theta. You have to get here, call this 2 pi, and you have to go pi over 6 past 2 pi. I think that would be 13 pi over 6. So you have to go from it, you can't go from 5 pi over 6 and then call that pi over 6. You have to call that a different name. Pi over 6 past 2 pi is 13 pi over 6. So this would be good. By the way, the question that you have, I think, on your assignment, be careful. Some of them are set up the integration only, which would be this. Except guess what? I've made a mistake. So I don't have to do the integration. I'm just setting it up. Set up the integration means set it up and stop. But there's a mistake here. What did I do? I went from 5 pi over 6 all the way around to 13 pi over 6. So I thought I left out the inner loop. But you know what? It didn't plot the inner loop. It did not plot the inner loop. But as you swept out sectors of area, if you remember. That's how it works. And guess what? You passed right over you did get the inner loop. Even though you didn't plot it out, those sectors of area sure swept right over it. So this actually includes the inner loop. This is this area. And I'd like to get rid of that. So maybe I should subtract we should subtract the area of the inner loop, which we started with by saying that would be from pi over 6 to 5 pi over 6. So that's kind of an interesting little problem. You thought maybe you were leaving out the inner loop by going with these bounds, but your sectors of area were sweeping right over it. You were getting the area of the inner loop, even though you thought you were leaving it out. So let's actually subtract it now. So there we are. So that's a good question. It takes a little thinking there about that. This is the accurate setup for between the loops. There's another way to do it. You could do, you know what you could have, well, yeah, whatever. I mean, you could just do the whole thing. If you do the whole thing, that's 0 to 2 pi is what I mean by that. Go from 0 to 2 pi. Just do the whole thing from 0 to 2 pi. You know, what happens then is you get this, which covers the inner loop. Then you actually do the inner loop. So you actually get the inner loop twice when you do from 0 to 2 pi. You get the inner loop twice. So then you could subtract 2 of them. Subtract 2 of these. So there's another option for a proper setup. Okay, that's enough on this video. That's enough, I guess. If you got any questions, let me know. Do some homework.